Very good afternoon to everyone. This is Professor Harish Mekli from BMS College of Engineering. Today we will discuss on the introduction to ARM instruction set. This is module 5 in Microprocessor and Microcontrollers subject for Computer Science Department and Information Science Department. Let's look at the syllabus first. What is there in the syllabus exactly? It's in the module 5. Introduction to ARM instruction set, data processing instructions, branch instructions, software interrupt instructions, program status register instructions, coprocessor instructions, loading constants, and simple programming exercises. This module 5 is taken from the textbook 2 in the prescribed in the syllabus. The textbook title goes like this: ARM instruction, ARM System Developers Guide by Andrews Loss and the Dominic and the White, published by the Elsevier in 2008 edition. This is in chapter 3, chapter 3, the topics from 3.1 to 3.6, but excluding 3.5, 3.5.2. This is what is there exactly the syllabus. In this, today we will discuss on, this is a agenda for today's lecture. Introduction to instructions, what is exactly an instruction means, and then we'll discuss on instruction set, and then we'll come to the execution. How does an instruction gets executed on a processor or on an ARM processor? What is the general syntax of an ARM instruction? And then we'll go to the classification of the ARM instruction set. In that classification, today we'll try to cover data processing instructions, in particular data movement instructions, arithmetic instruction, and logical instruction. If time permits, we will also cover the comparison instructions and the multiply instructions. Let's start with this. Introduction. What exactly is a program? A program is the information that we want to convey to the CPU or a computing engine. Like we human beings communicate with each other. We human beings communicate with each other using the words. Using these words, we will form the sentences, and these sentences together, we will write a paragraph, or we will convey the whole information to another human being. Now, if we want to communicate, communicate an information to a CPU or a computing engine, CPU has its own words which we call it as an instructions. For example, right now in this case, let's consider increment and add as ADD and INC as examples. Using this, we will form one function, or we call it in assembly, we call it as a subroutine, or using these multiple functions will form a program. Finally, this program is a combination of all these instructions using which we are conveying information to a CPU. Like this slide gives you the analogy between the normal English language and the CPU programming. Words in our language like sit and stand are instruction in the for the CPU. This is analogy. This is analogy. Instruction, increment and add. Sentences in our language are similar to the functions in the program. The paragraph in our language, or whenever I say R, it's English or similar kind of languages. Paragraph in our language, it's a program in the CPU. So this slide gives us overall information that if we want to communicate with CPU, we have to understand an instruction that CPU understands. Now, there are different ways to do this communication to the CPU. We classified this as in high level languages, medium level language, and the low level language. What finally that CPU understands is only and only machine level language. That's because it is constructed out of a transistor circuits. Let's take an example of high level language. High level languages are like it's similar to the English or similar languages. Example, I can say A equal to A plus B, then this A equal to A plus B is not understood by the CPU directly, so we need a translator in between. This translator which converts high level language to the machine level language, right now let's call it as a compiler or an interpreter. Similarly, there is a medium level language. Medium level language has this mnemonics like ADD add, SUB is sub, INC increment. Similarly, mnemonics, the medium level language has this mnemonics, and this is also called as an assembly level language. Example, add A comma B. Again, this add A comma B is very convenient for us to understand as a human beings, but like for machine level language, again it needs to be converted to for the CPU, again it needs to be converted to a machine level language. Hence, we need a translator called as an assembler in between. Now at the low level language, we have an opcodes. Opcodes are like operational codes. One example that I have taken, which does not necessarily, this is a very rough example, like we assume that like opcode 72 means add A comma B or A equal to A plus B. So this opcode we can directly write it to the machine in the machine level language. In the machine level language, it is in the hexadecimal, if I represent, it is 0111 0010, that is 7 and 2 represented in the binary of the hexadecimal version 72. So all these instructions, whether it is high level or the medium level or the low level, they say the same information, that like add the content of A with add the content of B, store the result in the A back. All the three, whether it is A equal to A plus B or add A comma B or 72, it conveys the same information to CPU, but CPU understands only 72 as a number, as an instruction. The rest of the things we need some translators as a compiler or an assembler in between. Now, with this general understanding of what is an instruction, now we will come to a point like what are the ARM instruction sets. Before exactly hitting what is an ARM instruction set, let's understand this point, that like an instruction is a basic entity of the program, like we have explained in the previous slides, using which we convey an information to a processor. In particular to the ARM, different architecture versions supports different instruction set. I will read it again. Different architecture versions support different instruction set. For example, what we are studying in our syllabus, it is ARM7 TDMI family of processors. This belongs to ARM architecture version 4T. This ARM architecture version 4T has its own instruction sets. Now these instruction sets are implemented by ARM7 TDMI family of processors. Hope this point is very clear. Every architecture version has its own instruction set. This instruction set is accepted by or implemented by ARM7 TDMI family of processors. Right? Now we'll go to the other point, like ARM7 family of processors normally operates in two states, actually three states, normally in two states. One is ARM state, which is 32-bit, another is a thumb state, which is 16-bit. In ARM state, it has separate 58 instructions, and in thumb state, it has separate 30 instructions. A programmer cannot use a thumb instruction when he is writing a program in ARM state, or a programmer cannot use an ARM instruction when he is writing the code in the thumb state. This changing or from the ARM state to thumb state can be controlled using a T bit in the CPSR register. Right? So totally, okay, I had mentioned you one more state. One more state is actually a Jagel state. That's actually a 8-bit state which is implemented or which is there in the ARM to support the Java code, but it needs a special software to enable and working through the with the Jagel state. Hence, I said ARM7 family of processors normally operates in two states, ARM state and thumb state. What we discuss exactly in this class or in this module 5 is we discuss ARM architecture version 4T instruction set that is accepted by ARM 7 family of processors in ARM state. We will not discuss about the thumb instruction set in this module 5. And then, like, to give a conclusion over the slide or a conclusion over this concept, ARM 7 family of processors is a 32-bit processors with 32-bit registers with 32-bit instructions. That is, every instruction in ARM processor is 32-bit in length. Right. So, just as a conclusion, ARM 7 family of processors from ARM architecture version 4T, which is working in ARM state, which is 32-bit state, which has 58 instruction. Right. Now, this slide is very important. ARM 7 family of processors can work in two states, as I mentioned before. It's one 32-bit state called as an ARM state, 16-bit state called as a thumb state, and each of them have different instructions. Core instructions in ARM state is 58 in number. Core instruction in thumb state is 30 in number. Conditional execution, this is one of the most important thing in the ARM processor. We'll discuss about this more in the coming slides. Right now, what we say is a conditional execution is possible with most of the ARM state instructions, but it is possible only with a branch instruction in thumb state. Data processing instruction can access the barrel shifter. Okay, barrel shifter is again one more very important aspect of the ARM architecture. In data processing instructions, access to barrel shifter and ALU can be done in a single instruction. I'll repeat again, data processing instructions, access to barrel shifter and ALU can be done in a single instruction. But in thumb state, separate barrel shifter instructions are there and separate ALU instructions are there. We cannot combine these two. Or there is no option that like combines these two. That's the right statement to make. Program status register, all of us know that it has a CPSR. In ARM state, we have a read and write privilege to the CPSR, but in thumb state, we can only have an read privilege, do not have a write privilege, or we cannot access the CPSR in the thumb state directly. When we come to registers, all of us, we know right now by this time, as we have studied in module 4, that like 15 general purpose registers are there with one program counter in the ARM state. When it comes to the thumb state, these 15 are splitted into 8 general purpose registers plus 7 higher registers. That makes it as 8 plus 7, 15 plus PC, right? So what this slide gives the information is ARM processors will work in two different states, ARM state and thumb state. In ARM state, there are 58 instruction. ARM state, it is a 32-bit state, has a 58 instruction. Most of the out of this 58, most of the instructions are conditionally executed, and you can combine, or we can combine the barrel shifter the instruction with an ALU instruction in a single instruction, or barrel shifter operation in ALU operation in a single instruction. And then like we have a read write privilege to the CPSR, and there are 15 general purpose register with PC. In the thumb state, it is a 16-bit state, it has 30 instruction. There conditional execution is possible only with a branch instruction. There are separate barrel shifter operation the instructions and ALU operation instructions. And we do not have an access, direct access I'm saying. We do not have a direct access to CPSR register in thumb state. And in the available 15 general purpose register in thumb state, they get split into 8 general purpose register plus 7 high registers plus PC. Right. Now we'll see like how exactly an instruction is executed on the processor core. This is a slide that connects us from the module 4 to module 5. I will show you the in details just in a moment. Whatever the program that we write, the program will be stored in the memory, ROM, from where the processor fetches the code. program whatever I say, it is finally into numbers, like one example that we have taken in the previous slide, that is 72. So what initially processor core does is, processor core generates an address when we reset or when we power up a processor core. Normally, I'm just saying normally, it will generate an address 0x00. I mean, it generates an address 0. In the memory 00, whatever the number is stored, that is fetched to the ARM the processor core. This is a very general process in any processor, or this is a very general process in the any processor core. Once that number comes to the processor core, the first thing that comes to the processor core is, most of the time or almost all the cases, it will be an instruction. Once the instruction comes to the processor core, what happens? We'll see to this diagram. Please see to this diagram. Once the instruction enters through this data bus to this is a processor core. This is the whole thing is the processor core. Memory we have not shown here. Let's assume somewhere here the memory is there. Once we say like processor core generates an address, this address register generates an address 00 from where some number is there. That number comes to the data here, through the data bus to the processor core, and that goes to the instruction decoder. Instruction decoder understands what is the meaning of 72. Like our example, in our example, we have considered it as an add A comma B. In such a case, instruction decoder enables register files and the ALU to do the add operation. And then like when next process goes, like address register generates a next address, and whatever the data is stored in the next address will come to the processor core through the data bus, and then gets stored in the register file. If it is required, it gets sign extended through this circuit, with the help of this circuit, sign extended, and gets stored in the register file. One more very important point that we have to remember is, ARM processor will work only on the register file. It will not work directly on the memory. Anything and everything that need to be processed using an ALU or this execution unit, we need anything and everything that can be processed using this execution unit, we need that information in the register file. This structure is called as a load store architecture. If we have to process or work on two operands, then that operand has to be there in the register files, right? This is called as a load store architecture. So now whatever the data we want to process will come to the register file. Then like it will go to the barrel shifter, depending on again the way the instruction decoder enables the barrel shifter and ALU or the MAC. It goes to the MAC or the ALU or the barrel shifter, then data gets processed. The result gets again stored back to the register file. This register file, barrel shifter, MAC and ALU, this forms the execution unit of a processor core. I will repeat again. We can exclude the register files, but like just for having a data to be stored somewhere. Execution unit in the processor core consists of barrel shifter, ALU and MAC unit. MAC unit is multiply and accumulate unit. Then like once the data is processed through this through these three modules, and depending on the instruction, the data the result is again stored back to the register file. The result is stored back to the register file. Now to transfer the data from this register file to the memory, we have store instruction, right? Okay, once this processing is done, to store back the result from the register file to memory, we have a store instruction, right? We will take one example in this, that is add. Please look at this instruction, example instruction, add RD, RN, RM, LSL #2. LSL stands for logical shift left by 2 positions. That's through the barrel shifter. That is logical shift by 2 position is connected to the immediate register, that is RM, right? So what exactly happens inside? RD equal to Rn into Rn plus Rm into 4. What it means? Why it is 4? Because anything logically shift left is multiply by 2. I am doing left shift by 2 times, hence it is multiply by 4. Multiply by 4 the content of the register Rm, then like add that to the Rn, store the result in Rd. This is what happens through this architecture. I will just conclude it over this slide, that like anything and everything that we write as a program gets stored in this memory. Processor core generates an address. Let's take an example. On reset or on power up, it generates an address 00. In 00, whatever the number is stored in this memory, that will come to the processor core, and the first and foremost whatever comes, it will be an instruction. So it goes to the instruction decoder. Now instruction decoder understands what exactly is the meaning of that number. That example 72 in our previous slide we have taken, that is an addition of A comma B. So that enables this register files or the barrel shifter or the ALU or the MAC depending on the requirement. The next time again the processor core generates the address using this address register and gets the data from the memory. That data comes to the sign extension circuit. If it is required, the sign gets extended and stored in the register file. Whatever the data we want to process, now if it is there in the register file, using the help of the execution unit, that is barrel shifter and ALU and MAC, this data stored in the register file is processed. The result whatever is generated stored back to the register file. We have taken one example as add rd comma rn comma rm lsl #2. That is nothing but like logical shift left by 2 position, which is nothing but multiply by 4. When that multiply by 4 applies to the register rm, right? So rm multiply by 4 added with rn, now store the result in rd. This slide is a slide that connects us from module 4 to module 5. Right. Now coming to exact ARM instruction general syntax. What will be the general syntax of an ARM instruction? Here is a general syntax. It is label, then the instruction, CC. CC stands for condition. We will come to that. S is a suffix that enables an instruction to update the CPSR flags. We will come to that again in detail. Operand destination, operand source 1, operand source 2, and this is barrel shifter operation. Now whatever is there in the flower bracket is an optional content. It can be there in the instruction or it may not be there in the instruction, but ARM general ARM general syntax provides all these possible options. Now one example, add is an instruction, EQ is a condition. We will come to that in detail. Right now we just mention it. Add, EQ is a condition, and S is a suffix that updates the flags in the CPSR register. Now RD, Rn, LS. This is the same instruction that we have taken in the previous slide. RD, Rn, Rm, LSL #2. What it does, RD equal to Rn plus Rm multiply by 4. We have discussed this. But here is a condition. What is a condition? If this will happen, RD equal to Rn plus Rm into 4, this will happen only and only if Z equal to 1. Z equal to 1 should be set by a previous instruction before execution of this instruction. Add EQS, before execution of this instruction, there should be an instruction before this which will set Z equal to 1. If that has set Z equal to 1, this instruction will execute. Otherwise, the RD will hold its previous value. It will not get processed. This is the beauty of the ARM instruction. The ARM instruction provides you the two beautiful structures. One is the conditional execution, the other is the barrel shifter operation. ARM instruction general syntax provides two very beautiful options That is, one is a conditional execution, the other is barrel shifter operation. Now we will go to the conditional execution. See, this is an example. Move, MOV, move is a normal instruction. Move R4, R5, copy the content of R5 to the R4. Now, this instruction can be appended with a condition called as EQ, and this makes this instruction to execute only and only when Z equal to 1. We will discuss more on this. What are the, see, EQ is one example of the condition, right? There are so many other examples. EQ stands for equal. EQ stands for equal. Equal, how do we find a equal? If two numbers are equal, then the Z flag in the CPSR register is 1. If we subtract these two numbers, what I mean to say is, if two numbers are equal, when we compare them or subtract them, Z flag in the CPSR will be equal to 1. When that is equal to 1, when Z equal to 1, move EQ R4, R5 will execute. Otherwise, if Z equal to 0, the move EQ R4, R5 will never execute. Now we will go to the description of conditional execution. All conditional executions are possible only and only because we have some conditional flags in the CPSR registers. These flags are N, Z, C, V. N stands for negative, Z stands for 0, C stands for carry, V stands for overflow. Overflow is a particular flag connected with signed operation. Overflow V is a flag connected with signed operation. The rest of the flags are mostly connected with unsigned operation. Like one example that we have taken EQ as an EQ. EQ is one conditional statement or one condition when that depends on Z equal to 1. Similar to EQ, there is NE. NE is a condition when Z equal to 0. Similar to that, there is a CS or HS. What is this? This is unsigned higher or lower. This is higher or lower. Lower, when I say, how do we check whether the number is higher or lower? This is based on the whether when we subtract the two numbers, whether the carry is set, then we say the number is higher. If the carry is 0, then the number is lower or it might be equal. Now, MI's condition stands for N equal to 1. N equal to 1 is actually negative flag. When a negative flag N equal to 1, the MSB of a given number is 1, then we call that number as a negative number. So that MSB is set to N flag. Once it is N is equal to 1, then the condition MI becomes true. If N equal to 0, then the PL becomes true. PL stands for positive or 0. Just to repeat or conclude this slide, EQ condition stands for equal, that is Z equal to 1. NE not equal, condition stands for Z equal to 0. Then there is unsigned higher, which is carry equal to 1. When we subtract two numbers, we will, if we get a carry, that means the number is higher. And the unsigned lower or the same. When we don't get a carry, or when that means there are two possibilities, that like the number is small or it is same. The MI, that stands for minus condition when N equal to 1, that is negative, for negative. PL stands for plus, that is N equal to 0, that is positive or 0. The N flag is just a representation of MSB bit of a given number. Right. Now there are other possible suffix as HI. It is an unsigned higher. LS, lower or same. It is again an unsigned operation. HI stands for, or HI looks at the flags C equal to 1 and Z equal to 0. That is, carry should be 1 and Z equal to 0, then like this HI condition becomes true. LS condition, carry should be 0, Z has to be 1, that is unsigned lower or the same. The other flags like combination of N and V will say the other conditional codes or conditional characters, GE, LT. GE stands for signed greater or equal, LT for signed less than, GT for signed greater than, LE stands for signed less than or equal. Like this, all these are options available for the condition here. Just to mention, move EQ is a conditional code. In this, in place of EQ, what all other options that we have mentioned are the one which are mentioned in this slide. Now, that's about the conditional execution. Now coming to the barrel shifter operation. Move R4, R5, it's a simple instruction that copy R5 content to R4. Now, LSL #2, logical shift left by 2 positions. This instruction can also be written as move R4, R5, LSL R3. R3 holds the value 2 now. That's the meaning. That means shift operation for the barrel shifter can be given as an immediate value or a register value. 2 possibilities. What happens exactly? R5 R5 content is logically left shifted by 2 positions and then like transferred to R4. We will see what are the other possibilities in the barrel shifter operation. This is a barrel shifter connection with an ALU. This barrel shifter is associated with the pre-processing of instruction. That is possible with only one operand, RM, right? And then it is given to an ALU. Then like ALU processes the result depending on the instruction or the input from the instruction decoder, and then like generates an RD. Now let's see what are the possible barrel shifter operations. See to this thing. Now in this, if there is a logical left shift, there has to be logical right shift. If there is a logical shift, there has to be an arithmetic shift. If there is a shift operation is available, then there is also a rotate operation is available. So let's see this in detail. First one, logical shift left by an immediate value. What is that? RM, LSL #shift immediate. That is, this is nothing but this example. LSL #2, RM, now R5 is RM there. RM, LSL #2, that's the meaning. RM, LSL, LSL RS, RS is a register content. Logical shift left by a register. Next, logical shift right by an immediate value. Logical shift right #immediate value. Logical shift right by a register, RM, LSR, RS. Arithmetic shift right by immediate, that is RM, ASR #shift immediate. Hope all of you are clear with the concept that like arithmetic shift is a concept when we shift right, we are preserving the MSB value of a given register content. That is, in this case, it is an RM. There is no meaning for an arithmetic left shift. Hence, there is only an option for arithmetic right shift in this barrel shifter, right? So, what it is doing? Arithmetic shift right by an immediate value, RM, ASR #shift immediate value. Arithmetic shift right by a register value, RM, ASR RS value. These two are for arithmetic shift right thing. I will repeat again. Arithmetic shift is to preserve the MSB of a RM register. In this case, it is an RM register, right? Which is a signed flag, or sign indicator. Rotate right by immediate value. Rm comma rotate right hash immediate value, rotate right by a register value, Rm comma ROR, Rs. Rs is a register value. Register has some value. By that value, the content of Rm is rotated right. There is no rotate left because rotate right is a complementary value for rotate left. So, if you want to rotate right, if there is a number is 8-bit number, if you want to rotate right by 3 positions, then you have to rotate left by 5 positions. I hope it is clear. If you want to rotate the register content, 8-bit register content, rotate right by a 3 position, then you can rotate left, same thing, rotate left by a 5 position. It will give or yield to a same value. Then there is one more option, rotate right with extended. What do you mean by extended? Or what is the syntax? Rm comma RRX. RRX stands for rotate right including a carry. Extended here means a carry. Right. Now we will go exactly to the classification of instructions or ARM instructions. There are actually like 7 types of ARM instructions or ARM instructions. First, data processing instructions. In that, we need to study data. There is data movement instruction, arithmetic instructions, logical instructions, comparison instructions, and multiply instructions. Second, there is a branch instruction. Third, there is a load and store instruction. This is very, very important. The load and store instructions has single register load and store instruction. There are multiple registers, can be multiple register load and store instructions, stack operations, swap instructions. Then we have a software interrupt instructions. Then we have a program status register instruction, coprocessor instructions, and loading constants. We'll see one by one in this list from now. First example, data movement instruction. Let's understand the syntax for a data movement instruction. Instruction with a condition. Now we are very clear what is this condition means. This condition means it might be EQ or MI or PL or CS or HS or CS, depending on the condition that we want to associate. We have listed these conditions in the previous slide. Then there is a S. S stands for, S is a suffix that is appended for an instruction. Only and only if you append this S to an instruction, then the CPSR registers, CPSR conditional flags are updated. What is that data movement instructions can do? If we append suffix S to move instruction, then it can update the carry and Z flag, right? That's about a S, and then there is a destination register, and then there is N. Now N can be a register by itself or it can be an immediate value. This is a general syntax. I'll just repeat it. The general syntax has instruction, condition, S, RD, comma RN. Yes and condition are optional. Hope it is clear. There are 2 instructions available in the data movement instruction. One is MOV, another one is MVN. MOV copies the content of N directly to RD. MVN copies the one's complement value of N to RD. We will take some examples and then understand in these 2 instructions in detail. Let's check these examples. Every instruction, see, this is one more thing that I have missed out. Every instructions can be associated with the barrel shifter in the ARM state. So what we do is here, we take both the examples of MOV and MVN instruction without barrel shifter operation in this slide, and in the next slide with barrel shifter operation. Let's consider a MOV R1, R0. What is this says? Before the execution of this instruction, R1 is 0, R0 is 4. After the execution of this instruction, R0, that is 4, gets copied to R1. After the execution, R1 equal to 4 and R0 equal to 4. Please note that most of the processor I am saying have only the copy option or have the copy option. It copies the content of R0 to R1. It is not a cut operation, it is a copy operation. Example 2, if initial content of R1 is 0, I can move the data immediately. So, move R1 comma hash 0x04. After the execution of this instruction, R1 is equal to 4. R1 gets a value 4. That is an immediate transfer. Example 3, now this is very important. Hope if you can recollect the previous slide, you can answer this thing. R1 is 0, 0 initially, R0 is 4. MVN R1 comma R0 means it takes the ones complement of R0 content and transfers that to the R1 content, and R0 content remains as a same value. What will be the answer for, or what will be the content of R1? Can you guess? Yes. The content for R1 is, you have to take a ones complement of 4. Ones complement of 4 in 32-bit value, it is FFF, 7 Fs in the last nibble, it is B. That is ones complement of 4 is B. So, after the execution of instruction MVN, R1 has a ones complement value of R0. Right. Now, we will see like what are the instructions with the help of barrel shifter. Same instructions, we will take MOV and MVN instruction, we will associate them with the barrel shifter operation. MOV R1 comma R0 comma LSR hash 1. This means logical shift right by one position. So, logical shift right means, logical shift right means divide by 2. Logical shift left means divide by, multiply by 2. I will repeat it again. Logical shift right means divide by 2. Logical shift left means multiply by 2. In this case, before the execution of this instruction, R0 has 4 value R0 value is 4, R1 is 0, 0. After the execution of this instruction, R0 value holds the same value as previous or before the execution of this instruction. What will be the content of R1? R1, logical shift right by one position. This applies on register R0. R0 content is 4. 4 shifted one position right is divided by 2. That answer is 2. That answer, this whole R0 LSR 1 holds the value 2. This 2 gets transferred to 1, R1 now. Hope this is clear. Similarly, can we do the second one, or like in the next example? Next example is that R1 is 0 again, R0 is 4. MVN, in place of move, there is MVN now. R1 comma R0 comma LSR hash 1. That is logical shift right by one position, the content of R0. The content of R0 should be logical shifted right by one position. That if we shift, right now R0 holds 4. If we shift 4 by right one position, it is 2. And you have to remember MVN takes ones complement of that value. So, ones complement of 2 is the answer that gets stored in R1. That 2 ones complement of 2 is 7 Fs followed by D. Hope it is clear. Right. Now, those are the only 2 instructions that are available in the data movement. Data movement instruction, move and MOV and MVN. Now, we will go with arithmetic instructions. There are 6 possible arithmetic instructions available in ARM7 or ARM7 family or ARM architecture version 40. The general syntax of this instruction, arithmetic instruction, is instruction with a condition, again suffix S, RD, Rn, N. Now we'll take a particular example. Now we'll study like what are the possible instruction in this. There is an instruction called ADD add. What it does, it adds the content of Rn in the according to general syntax. If you see the syntax here, Rn with n and stores the result in Rd. ADC, what it does is add with carry. Rd equal to Rn plus n plus C. C stands for carry flag in the CPSR register. SUB is a subtract instruction. What it stands for, Rd equal to Rn minus n. Content of register Rn is subtracted with n and stored in the Rd value. SBC is subtract with carry. Rd equal to Rn minus n minus 1's complement of C. RSB stands for the reverse subtraction. That is, in the previous case SUB it is Rn minus n, in RSB it is n minus Rn. RSC stands for reverse subtraction with carry, that is n minus Rn minus negation of the carry flag in the CPS. We will take some examples of this and let us try to understand in detail. Yeah, the first example, R2 holds a 0 value, R1 holds 4, R0 holds 3. R1 holds 4 and R0 holds 3. Add R2, R1, R0, that is content of R0 and R1 should be added and the result is stored in R2. Content of R0 and R1 is added and the result gets stored in R2. Yeah. After the execution of this instruction, it is 4 plus 3 is stored 7. 7 is stored in the register R2. R1 and R0 holds the previous values. Example 2 is subtraction of the same previous conditions, that is R2 equal to 0, 0, 0, R1 equal to 4, R0 equal to 3. If we execute this instruction, the result will be R1 minus R0, the result is 1, 1 gets stored in R2, that is what we have written here. Now this is important. What is this? These two examples, example 1 and example 2 are pretty simple and direct. Example 3 is one which is very important or very much available mostly in ARM. R1 is 4, R0 is 3, R2 is 0. RSB, that is reverse subtract R2, R1, R0. What happens in here is it is reverse subtract, that is R0 minus R1 will happen. That R0 is 3 minus 4 is the result is minus 1. The minus 1 in here it is a 2's complement of the value. Minus 1 in ARM is represented using 2's complement value. 2's complement of minus 1 is all F, 8 F's representing the 32-bit register value. Hope this is clear. The reverse subtract 3 minus 4 is minus 1. Minus 1 is represented in the 2's complement. That's where the R2 holds the value all F. Now this is the next one. Example 4 is that like this slide was without a barrel shifter. In this slide we will take with a barrel shifter. R2 is 0, R1 is 4, R0 is 3, again the same as the previous condition values. Instruction here is add R2, R1, R0, LSL1, logical shift by 1 position, R0. The register content of R0, that is 3, is logical shifted by 1 position, that is multiply by 2. Logical shift left is multiply by 2. So R0, that is 3, gets multiplied by 2. The 6 get added with R1 content. R1 content is 4. 6 plus 4 is the value is A. A in hexadecimal is 10 in the BCD. Now example 5. Again this is a slight change in here. What is that? R2 is 0, R1 is 4, R0 is also 4. R0 is also 4. SUB R2, R1, R0, LSR, this time it is logical shift right by 1 position. What is the logical shift right? Logical shift right by one position is divide by 2. So R0 content, that is 4 divided by 2, will give you 2 as a result. That 2 has to be subtracted from R1. R1 minus 2 is the result that is stored in the R2. Right? Can you guess the result? Just a 2 thing. Done. Right? Okay. Done.